In this video, I'm going to talk about Moore's Law. In case you missed it or you just want some more info, you can't get enough of CIS game design. Who is Gordon Moore? What is his law? Well, let's learn about Gordon Moore. There's Gordon Moore on the left. In 1965, he was the research director for Fairchild Semiconductor. There he is on the right in 2012. And he was interviewed by Electronics Magazine about where he thought the electronics industry was going. But in order for that, his prediction to make sense, we need to talk about the transistor. The transistor is the building block of all modern digital electronics. It is a little switching element, and you can combine them together to make circuits that add and subtract and compare and do all the things that CPUs do, or modern electronics, particularly computer chips, need to do. Now, when we make these microchips, the transistors are microscopically small. However, some mad genius decided, I want to build a CPU out of regular-sized transistors and see what that looks like. Now, let's look at some transistors here. So this is a computer that I am currently in the process of upgrading. This is an Altair replica, and you can see those little black things between the LEDs down here at the bottom. Those are all transistors. These are all transistors, these little black things down here between the little LED posts. So that's what you were seeing in that picture. Now, when these go into computer chips, they are all microscopically small. But what would happen if we built a CPU out of the regular sized transistors that were not microscopically small? What would that look like? Well, that's the Monster 6502 project. So let's go take a look at that. Here's the Monster 6502 on YouTube, and that is about 3,500 transistors all on a board. And the FAQ for that is very funny. Somebody said, if you used those transistors to make a modern CPU, how big would it be? And he worked it out, and the answer was in hectares. It would just be absolutely enormous. But the key takeaway here is that transistors are the building blocks of modern electronics, and we can manufacture them at microscopic size in our computer chips. Gordon Moore also is the co-founder of a company you may have heard of. He left Fairchild Semiconductor to start a company that was going to be called Integrated Electronics. They decided, that's not catchy enough. Let's shorten that to Intel. So he is one of the co-founders of Intel. So he is a very, very wealthy man indeed. So let's get back to Moore's Law. What was this? He had this interview with Electronics Magazine. Where did that go? What came out of that? Well, they asked him, what direction do you think the electronics industry is going? And he said, way back in 1965, I think transistor counts are going to double every year. That means the number of those microscopic transistors that we can put in a chip is going to double every year for the next 10 years. Later, he revised that down to every 2 years. So that was his prediction about every year or every 2 years, we're going to be able to pack twice as many transistors into a chip. And what impact would that have? Well, we could expect that a RAM chip would be able to hold twice as much memory. Maybe our CPUs would get twice as fast. Maybe costs would drop. The answer is yes, all of these things. So Moore's Law has actually, how well it's held up, we're going to find out. So does Moore's Law hold up? It has actually held up almost. It has held up surprisingly well. It's been very, very accurate by and large. Now, there's reasons for this. Moore's Law is not really a law of nature like gravity. It was a prediction, but the industry sort of took that as its guiding principle and said, we have to design hardware at a pace that Moore's Law would predict. So Moore's Law is seen as a target by the hardware industry and not as this kind of just, an off-the-cuff estimate from some guy from 1965. Now, where does the doubling come in? Why doubling? Well, part of it is the people will learn how to make things, the manufacturing process will improve and we can get more, and that's why we'll be able to get more chips together. But why do we go from 8-bit computing to 16-bit computing rather than from 8-bit computing to 9-bit computing? Well, imagine I had an 8-bit CPU and I had another 8-bit CPU, right? Rather than designing a 9-bit CPU, wouldn't it just be easier to kind of, chain two 8-bit CPUs together and make a 16-bit CPU? The answer is yes. So that's why, we don't just add one more bit. We take something that already works and we kind of double it and we clone it and we wire it together. So that's where the doubling comes in. With complexity. Now, Gordon Moore himself is actually amazed at how well his prediction has held up. He said, frankly, I didn't expect it to be so precise. So it was just an off-the-cuff, or I wouldn't say off-the-cuff, it was an educated guess based on his knowledge of the semiconductor industry back in 1965. But the hardware industry has taken that, and it's kind of their guiding principle. It's their target that they try to meet. So it has kind of become true because people want it to become true. Now, Moore's Law is kind of fun to play with, at least in a historical context. It is fun to go back and look at some old computer magazine and see that, people say, wow, I can't believe everything costs so much. I mean, computers were thousands of dollars. Everything was so expensive. And now, and the performance is so much less than what you get now. So let's do some exercises here and just kind of see how prices have changed over time. I mean, here's a 250 megabyte hard drive from 1979. The thing looks like it's made out of wood. I don't know. That looks like, I can't believe that's a hard drive, but apparently it is. I mean, and now that's, most people are walking around with like terabyte USB sticks. So, I mean, it's amazing how much more miniaturized things have become. Let's take a look at this 32 gigabyte SD card. Let's see what that would have cost in 1983. Well, let's look at how do we figure out what memory cost in 1983? Well, I was leafing through this magazine, and I saw this 64K of memory for $129.95. Now, that 64 and 128 are, they're just power of, they're just multiply by 2, and you can turn 64 into 128. So let's just assume that this is $128 and not $129.95. That is about $2 per kilobyte. $2 per kilobyte of memory. So at $2 per K, or $2 per kilobyte, what would this 32 gigabyte SD card cost? Well, drum roll please, $64 million. I cannot believe it. So yes, if you were going to try to buy this much memory in 1983, it would cost $64 million at $2 per kilobyte. We can go the other way too. Like we could say, all right, look what this thing is, what does this thing cost, and what is it per kilobyte? And it actually, I worked it out, it works out to about 2 thousandths of a cent per kilobyte. So you can see what memory cost went from $2 per kilobyte down to 2 thousandths of a cent. So you can see there's the cost coming down over time. Moore's Law has some important implications for design. Imagine you are trying to push the envelope and you're trying to design something new, innovative, that requires a lot of processing power, a lot of capabilities. The hardware that you have at your disposal may not be up to the challenge. But that doesn't mean you should stop designing. You should give up that project, because Moore's Law has your back. By the time you develop that project, by the time that thing becomes a commercial reality, the capabilities of the hardware may be there for you. The performance will come up, the cost will come down, and that thing that is now very, very expensive in a few years may become a very affordable consumer electronics device. So if we apply Moore's Law to the HoloLens, right? So now it's $3,000. Next year it'll be $1,500, and it'll just keep dropping. So to the point where now anybody who wants a HoloLens, can go buy one at Micro Center. So we should all be very thankful to Gordon Moore, because thanks to Gordon Moore, all that really awesome gaming hardware will eventually become affordable.